I want to do another example of accurately graphing a transformed sinusoid. In this case, we have this cosine equation, cosine function that we want to graph. And first I'm going to put some axes down here. I'm going to put theta axis along here and a y-axis this way. Actually, I'm going to move this particular graph is going to be mostly in the negative zone, so I think I'll move this up a ways. Okay, so the first thing we're going to put down, remember we have these different numbers. We call this C. This is we usually use the letter C for this value out here in front, the -4. And that is the sinusoidal axis. So that's the first thing I'm going to put on my graph is, and I'm just going to kind of eyeball, I'm just going to decide that this place right here is -4. Maybe I'll move that up a little bit. But I'm calling that -4. And that red line is the sinusoidal axis. And then I'm going to mark just a couple other places here. That would be -2, and this would be -1. Let's move these things around a little bit. I don't like those. I'm trying to make a pretty accurate graph here, so let's try to be accurate. -2, -1. This would be -3. I'm actually using my fingers on the screen to figure out where these other points would be. That would be and about there. Now, I'm just going to label the points that I'm interested, label the values on the y-axis that I'm actually interested in, which are -4, right here. That's where the sinusoidal axis is. And -1, that's where the maximum is going to occur, because I can see in my equation that the amplitude is 3. That's what the 3 is out there in front of the cosine. And that means that my graph, that means my vertical dilation is by a factor of 3. And so instead of going up 1 above the sinusoidal axis and down 1 below the sinusoidal axis, it's going to go up 3 above the sinusoidal axis and down 3 below the sinusoidal axis. I am going to put lines there for a maximum and for a minimum at -7. That's the interesting stuff that I really need on the y-axis, those 3 lines. I don't have to put in lots of other scale factors. Okay, now the more challenging part usually is figuring out some stuff in the horizontal direction. I can see that there's a phase displacement of 7. That's the theta minus 7. 7 is the value for theta. That'll make the argument 0. And the 6 in front of those parentheses, that's all part of the argument, 6 theta minus 7. The horizontal dilation factor is 1/6. That is the way things work. That's what we learned in chapter 1 about how things work in the horizontal direction. Whatever is out there in front of theta is going to be the reciprocal of that for the horizontal dilation factor. Well, that is 1/6. The normal period is 360. So I'm trying to figure out one period now. 1/6 times 60, or 1/6 times 360 is 60. That is going to be one full cycle. I think it's going to go from a maximum at the beginning to another maximum 60 units later. Another thing that I'm really interested in, though, is 1/4 of the period, because that's where maximums and minimums and crossing the sinusoidal axis, which we call inflection points, that's where those important things occur. And we can just get those dots on this graph, then we'll be able to draw a really nice graph of this. So that is 15. Now, in some of the other examples, we talked about finding the greatest common factor between 1/4 of the period, in this case, which is 15, and the phase displacement, which is 7. Well, the greatest common factor between those two numbers is 1. But I don't want to make a scale that goes 1, 2, 3, 4, 5, 6, and out to 60. That's just not fun. So I'm not going to do that. And those numbers aren't that important. So one reason I'm not doing this on graph paper is because I want to just kind of be able to eyeball it. I still want to do a nice accurate job here, but I'm just going to put down a place on the theta axis. I'm going to call that 7. Okay. Now, I want to go out 15 units further. Now on my screen, that's about 7 is about 1 finger's width, and 15 is about double 7. So I'm going to go out 2 fingers widths and a little, maybe just a slight bit more, and that is going to be where 22 is going to happen. All right, 15 plus 7 is 22. Then that's 2 fingers widths, and now I'm going to put a dot there. You could use a ruler and make this pretty accurate, but you can also just use your fingers. You can't see me doing this, but that's what I'm doing on my computer screen right now. And so my spacing is pretty good. And I'm also going to go over in the negative direction and put a couple of values over in this direction. Okay, those what I have there are places where the interesting things are going to happen. So that is going to be, see if I can actually add these numbers. So 22, make a bunch of these things and I'll just change the values here. 22, 37 is another 15 away, 37, 52, 67, and what's that going to be? 82. Hopefully I've got these numbers right, my addition and subtraction. And this doesn't look very good. This doesn't look very accurate, does it, over here on this side? That's supposed to be -8 because it's 15 away, but that, see, my scale's not perfect. One more in this direction, and that would be -23. Okay. So I'll cheat a little bit. I'll move that point over a little bit. So that's better. Okay. All right, now a cosine starts at its maximum at the phase displacement. So I'm going to put my first dot right there at 7. And then I just have to count over 15, which is 22, and put a dot on the sinusoidal axis. And then I count over 15 and put a dot at the minimum. Then I count over 15 and put a dot at the sinusoidal axis, and then at the maximum, and then at the sinusoidal axis. So we're trying to make this into just a connect the dots game, and it works pretty well if you do the preliminary work. Okay, now I just have to connect these dots, and I'm just gonna, I'm doing this with a mouse, so I think I can come up with a pretty good graph this way, but won't be great. If I had a pen, so that's a pretty good graph. Looks not bad. You can see all the important things: maximums, the minimums, the points of inflection on the sinusoidal axis, and we're done.